Hello, welcome at the second session this week. Thank you for joining me. I hope everybody is well. Okay, hello, thank you. Okay, because it's quite late, let's don't waste time, let's start. That means, yes, good evening. This session will be about section 3.3 and we will talk how derivatives affects the shape of the graph. We did cover yesterday minimum and maximum value of the function and especially the critical points, okay? Section 3.1 and 3.2, you will have the video. It's just one theorem, quite important in mathematics, mean value theorem, but you will have the video about this. But let's focus on shapes of the graph and how derivative affects this, okay, for tonight. So let's see what I have. Probably lots of things that I will cover tonight. It's quite known. Okay, that means let's just put nicely everything together. Okay, that means for example, okay, we will check. First of all, we will check the first derivative. But you probably remember because we were saying we were defining this. If function. Shall I draw it? Yes, I can actually draw here. If we have function like increasing, what we can say about the slope of the tangent at actually every point on this curve. Like if I will pick a point here or here or here, yeah, this is function f of x, let's say, and then I mean for any, and I will draw a tangent, another tangent. What we can say about the sign of the slope of the tangent line? Is yes, that's my point. The slope is positive, okay? That means every single slope is positive, and of course, slope of the tangent, it's simply the derivative. And the shape of the function or like one of the property, can we say that function is increasing or decreasing? This function that I just draw it, that function that you see, f of x, is increasing. Okay, that means this is actually one important feature. When the function is increasing and the derivative exists, of course, always the derivative will be positive. Okay? That means in order to find an interval where the function is increasing, we have to find the derivative and say it's greater than 0 and solve it. And of course, respectively, the same for decreasing. And let's see, because I do have the graph of the function, we can see we have the graph, we have a few points. Maybe I can just ask you a few questions and check if you understand the yesterday section. Like, can you tell me, I think A, B, C, and D are the values, are the y values. That means what is the absolute maximum value of this function? It's D. Okay, thank you, it's D. What about absolute minimum value of the function? It's A. Okay, I'm just looking at the yes, thank you. And okay, what about local maximum value? It's at the point B, I mean it's B. What about D? Can we call D locally highest point? Do you remember? No, thank you. Because we remember the endpoints, we will not define like locally. Yes, Jack, thank you. Because we don't know what's going on the other side. We really have to have two sides of the story. Yes, yeah, okay. That means we will not call local. But highest, absolutely lowest, we don't have to really look on the other side. Okay, and of course, locally lowest point, local minimum, Can you just tell me? It's C. Thank you. Okay, that's you good with this. And now let's look how derivative affects the shape. Of course, I'm saying about increasing, decreasing, and you see my tiny tangent lines, and we can definitely see that the slope is positive from A to B and from C to D, and then derivative is positive, which means function is increasing. Yeah, just the conclusion. Now from B to C, that's the only like interval, the slope is negative, derivative is negative, and function is decreasing. Okay, that means this is the information about the connection between the graph, the shape of the graph, and the first derivative. Okay, so now we can see, and this is just here increasing, decreasing test. If the first derivative is positive, function is increasing. If it's negative, function is decreasing on that interval, of course. Okay, and now let's take a function, just polynomial, no fancy formulas, no fancy expression, no rational functions, no denominators. And that we have polynomial function, each number is in the domain, and because polynomials domain are all of the real function. And now we have to find an interval for the increase and decrease. Okay? Find where the function is increasing and where the function is decreasing. That's what we have to do. We have to find out the derivative. Okay? And then derivative is positive for the increase, negative for the decrease. Okay. I can maybe, you probably know the derivative, but let me ask you, can you type for me derivative of this part? What's the derivative of 3x to the power of 4? Just testing. Yes, 12x cubed. Thank you. Can you type for me the derivative of negative 4x cubed? Negative 12x squared. And what about negative 12x squared? What's the derivative of the third part that I circle? Negative 24x. And what about the derivative of 5? 0. Okay. That means I do have, I did add all of my, I think I have the right derivative, and we can see function is increasing if the derivative is positive. That means what we have actually, we do have a third degree polynomial inequality. Okay, that means now, in order to finish this question, we really have to know our algebra. That's what we can do. We definitely need the product form, because having a product form, we will see the zeros. And what do you think? Shall I factor out a common factor first? Because we would like to solve this. Of course, I will keep 0 on this side. Yes, the 12x is the common factor. I did factor out 12x, and then x squared minus x minus 2 stays. Now we have quadratic expression. Do you think we can factor out this one easily? X squared minus x minus 2. I did type it. That means I will erase 2 and 1. Okay, John is telling us negative 2 and positive 1, and I think this will be correct. Oh, I do have it. Okay, and now what we need? We need the zeros. That means we know that 12x will give me 0 if x is 0, x plus 2 will give me 0 if x is negative 1, and x minus 2 will give me 0 if x is 2. That means I do have this, but this is still not the solution. Yeah, we remember inequalities. I have to place the zeros on the number line. Okay, I did. Okay, and now I think, okay, I didn't. Okay, I will. Now we have to test each subinterval. And what we're looking for? We're looking for a positive, the left-hand side, which is product of these three factors, this product must be positive. Okay, that means what we will do, and I just list all of these factors. Okay, that means from negative infinity to -1 is the first subinterval, and we will pick the test value -2. When I substitute -2 here, 12 times -2 is negative, -2 plus 1, negative, -2 and -2, negative. Negative times negative times negative will give me negative. Okay, that's not what I'm looking for. That interval is not my solution. Okay, between -1 and 0, actually it's a tiny, let's take -half. Yeah, because it's tiny subinterval. Okay, -half times 12, negative. -half plus 1 is actually positive. -half and -2 is negative. Negative times positive times negative will give me positive output. And then between 0 and 2, 1. 1 times 12, positive. 1 plus 1, positive. 1 minus 2, negative. Positive, positive, and negative, when I multiply, will give me negative. And then let's take 3. 3 times 12, positive. 3 plus 1, positive. 3 minus 2, positive. 3 times positive will give me positive. That means positive, it's my answer. That means the answer will be, an interval will be from negative infinity to 0 and from 2 to positive infinity. This is for the increasing. That means we can say that the function is increasing if x is from negative infinity to, from -1 to 0 and from 2 to positive infinity. Okay? And of course, the negatives will give me the decreasing interval. Yeah? But we can see it's nice inequality. Okay? And I actually I have the table. I just put the other way because I think that's the way that they did in your textbook. But we can definitely see. I'm just trying to, from negative infinity to, why I'm saying negative infinity? From -1 to 0, because this is the graph of the function. From -1 to 0, function is increasing, and from 2 to positive infinity. Okay, and then the other intervals will give me decrease. Okay, yeah, really nice. Let me just, okay, hang on. I would like to do one thing with you. Let me possibly add, because I just need one slide. Before I show you the next property, you will probably tell me. Okay, that's mean what just one more time. -1, 0, and 2. That means what we had. Let me just, -1, 0, and 2. That was the zeros of the first derivative, right? That was the zeros of the first derivative. And we did get negative, positive, negative, positive. That means now what we know about the function. When the first derivative is negative, we know that the function is decreasing and then increasing. Okay. Oh, I don't know which way to bend it. Maybe I shouldn't, because that's another thing. Function is decreasing, increasing, decreasing, and increasing. Yeah, just the really, how can I say, primitive explanation, yeah, graphical explanation. But -1, 0, and 2, that's the solution of this equation, right? Derivative is 0 if x is -1, 0, and 2. And do you remember what is the name of these zeros of the derivative? How we call these numbers? from yesterday. Critical points, critical numbers. That's critical numbers. Okay. And now you remember yesterday when we see the graph and when we see the local maximum or local minimum, we know that this is happening at critical points. But now it's the other way. We do have a critical points, but we don't know if the function attains maximum or minimum at these points. Knowing this property, then when the derivative is positive, negative, increasing, decreasing respectively, we can nicely see. That means let's investigate the first situation, the first critical point. What do you think at -1, what is happening? On the left-hand side, function is decreasing and then increasing. That means what function does at -1 in terms of the local extreme values? Does function attain minimum or maximum? Yeah, we can nicely see it's a local minimum. Yeah, because we can nicely see that the bottom of the valley. I think yesterday somebody said the valley. Yes, that we can nicely see. It's like a locally lowest point. That means we will have local minimum value at -1. And what about at 0? On the left-hand side, function is increasing and then decreasing. We have this situation. What is happening here? Of course, we will have local max at 0. Yeah? And of course, what is happening at 2? We know the increasing, decreasing, local minimum again. Thank you for typing for me at 2. Okay, and actually that's the reason that I add the page, and even if I said it's, how can I say, so basic and so intuitive and so even primitive like drawing, that's actually the first derivative test. Okay, like if you will say if you will end up having a question or you have to use, like somebody will say, please use the first derivative test, determine the local extreme values. Yeah? That's what we have to do. We have to find out the intervals of increase and decrease, and we know what is happening at the switching point, yeah? Exchanging point. Decreasing, increasing, of course, minimum. Increasing, we climbing, and then decreasing, of course, maximum. Yeah, okay. That's it. Half of the section. Yeah. Critical points, I just ask you this. And then this is the first derivative test. Yeah. Probably I don't have to explain everything. I just type nicely, I believe, but we can see. Local maximum when the derivative is positive, negative, and local minimum if the derivative is negative, positive on the left, right-hand side, respectively. Yeah, that's what we have to do. Yeah, nice. And also, you remember, especially, yeah, the nice example x cubed. Even if we have critical point, we may have a situation that no extreme value is happening at that point. Yeah? Not all of the critical values will give me the extreme points. And of course, the good example is x cubed. Okay, because what's happened when we find out the derivative is 3x squared, and the critical derivative is 0 if x is 0. That means this is critical point, and we do have a horizontal tangent, but what's happened? Derivative is not changing the sign. Let's see, that's 0. Yeah, let's test. Let's test where the function is increasing when it's decreasing. That means when I put 0, my test value could be -1, and I'm testing the sign of the derivative. That means I'm testing that formula. -1 squared will be positive, times 3, positive. And when I substitute 1 squared, of course, positive, times 3, positive. That means we can see function is increasing and then increasing. Yeah, of course, we know the graph of, I can even draw maybe the graph, and I can move the function properly. Yeah, because of course, we have to know where is the value, but we can see function is increasing and then again increasing. Yeah? No extreme values. That we have to always check the sign of the first derivative. Okay. That means this is just the summary. We may have extreme values or we may not have it. Okay, and actually we did this question because before I even introduce, I ask you and you just tell me that, I mean, this is the same, yeah, the same function. That's the zeros, I mean the critical points, and we test it. Yeah, we test it for the local minimum and maximum. So we can skip this. Okay, let's do this question because this asks for the local extreme values, but it's the trigonometric function. That's me. Let's see if we can manage. We will do the same, yeah, the same way, we will follow the same algorithm. Find the local maximum and minimum value of the function x plus 2 sine of x. And just between 0 and 2 pi, because it's periodic function and we don't want to repeat the values. Okay, that's what we have to do. We have to find out the derivative first. And who can type for me the derivative of x plus 2 sine of x? I'm just looking at the chat box. I know that you're typing. We have lots of students and I'm really, really happy that you joining me. Derivative of x, you know derivative of x, yes, 1 plus 2 cosine of x. Thank you, Noah. Thank you, Josh. Thank you, Jack. Who else? I can wait. More, Justin, thank you. Robbie, thank you. John, thank you. Okay, yeah, it's nice to participate. Of course, I wish to like see you, all of you, and yeah, but it's fine. As soon as you type, I know that you with me. Okay, yes, I do have the same, 1 plus 2 cosine of x. And now we have to find out critical points. Yeah, that means let's because the critical points are critical situation are changing at these points. That means derivative is 0 if 1 plus 2 cosine of x is 0. Now we have not polynomial, we have trigonometric equation. We will solve this equation for cosine of x, which I will subtract 1 and divide by 2, negative half. And now the unit circle. Cosine for what angle is negative half? Who can tell me this? Pi over, no, I was going to, okay, pi over 3, which is 60 degrees, pi over 3, it will be for the positive half. Oh, no. Why we writing pi over 6? I mean 6 in the denominator. Robbie and John said the same. Okay, let me write down cosine for what angle is positive half. That means I think it's pi over 3. And also 5 pi over 3, because cosine is positive in the first quadrant and the fourth quadrant. Correct? That means this is different equation. Am I right? Yeah. Okay, because you both of you said pi over 6 and I sometimes yeah. That means we know we have just a few, really few trigonometric values, cosine, sine and tangent for 0, of course, 30 degrees, 45, 60, 90, and then the other one, but that's the main, the special angles. Okay, that means this is the first quadrant and the fourth quadrant. Now we need the second and the third. That means 60 degrees. What's the reference angle for the 60 degrees in second quadrant? Or how many times I have to multiply 60 to reach second quadrant? 2 times, right? 2 times 60, it will be 120. And this is the second quadrant. And 4 times 60, I will reach the third quadrant. That means 2 pi over 3, yes, yes, and 4 pi over 3. Thank you. Thank you for typing this. Okay, that means these two values, for these two angles, cosine is negative, and it's negative half. Okay, that we do have this trigonometric values. Oh, I didn't finish, but let me, now what I will do, did I finish this question? Okay, I do have the graph, but let's do it here. I mean, I will put 2 pi over 3 and 4 pi over 3. And we do have limitation because we have everything between 0 and 2 pi. That means we basically have 3 intervals like that. Now let's test, I will use the green color, let's test the sign of the derivative. That means we will test the sign of this, okay? Because this is my derivative. Okay, between 0 and 2 pi over 3, I have to pick a value, test value, test point, and I think 90, yes? Pi over 2 will be a good number. When I substitute to that box again, okay, let's see what sign I'm getting, because we know positive derivative, function is increasing, negative derivative, function is decreasing. Okay, pi over 2. Cosine at pi over 2, what is the cosine of pi over 2? Cosine of 90. 0, and 2 times 0, 0 plus 1, positive. Okay, now I can pick pi. And I think I can pick 3 pi over 2. Nice values, yeah? We will get 0, 1. Okay, pi. Cosine at pi, again, I am testing the sign of the derivative. Cosine at pi is negative 1, thank you. Negative 1 times 2 is negative 2 plus 1, negative. Okay? And then 3 pi over 2, cosine at 3 pi over 2, I think it's 0 again, thank you, John. And times 2 plus 1 will give me positive. Okay, so now how function behaves. Function is increasing and then decreasing and then increasing. Yeah. And what is happening at, local maximum? Local maximum is happening at which point? 2 pi over 3 or 4 pi over 3? 2 pi. Local maximum, and of course I just feel silly to ask you because it's so simple question. Local minimum will happen at 4 pi over 3. Now we can even see nice the shape of the function, almost. Yeah. Okay, that means that's the way to test for the local extreme values. We can maybe find, let's see, local, because we actually have to find local maximum and minimum value. That means local maximum, it's happening at 2 pi over 3. Now, in order to get that value, that we remember that horizontal line, I will use a function, yeah, to get the, which actually I have to put 2 pi over 3 plus 2 times sine 2 pi over 3. Oh, the number will be crazy, but let's at least, because it's radians, okay, I will keep this. I just wanted to for you to get this information. What is the value of sine of 2 pi over 3? This is second quadrant, of course. Sine is positive, but what is the value? It will be, oh no, it's square root of 3 over 2. However, we did have times 2, we can simplify. That means 2 pi over 3 plus root 3. If we will use the calculator, we will have approximately the value, but we can leave it like that. Yeah, that means this will be the maximum value. And respectively, the same, the minimum value is happening at 4 pi over 3. And we can substitute, because now my point is, in order to get the actual value using the original function. But all of my green symbol, like positive, negative, we were testing the derivative, okay? Because sometimes we don't know which formula we're using. Okay, 4 pi over 3, sine of 4 pi over 3. 4 pi over 3 is from the third quadrant. Actually 4. It means the value is the same, but it's negative. I mean the magnitude. It means this will be 4 pi over 3 minus root 3, because we can cancel this. Okay, that means this will be the local minimum value. Okay, and I think I do have, oh yeah, we can see I did even use the calculator. And this is local maximum and local minimum. Yeah. John, did you type negative 4 pi over 3? This is positive. That's the angle. That's, we don't even, no. We don't say value of the sine function for 4 pi over 3 is negative. But this will not change the sign. I'm not sure if this is your typo or you thought that we have to put negative. Yes, yeah, we don't have to change the sign of the angle, the sign of the corresponding trig function, yes, but not the, okay, that's, we did quite challenge question. Okay. Oh, okay, I see. No, just, yeah, positive. Okay, that's me. Now let's look at the second derivative, okay? Because we have to like investigate how the second derivative is affecting the graph, or maybe the other way, how graph is affected by the second derivative, yeah, whichever way we look. Okay, let's look at these two blue curve, yeah, from A to B, That's mean curve F and curve G. We can see both of them are increasing. That means no problem. We know that the first derivative is positive. Yeah, that's not a problem. But do they look the same? Or it's something different? Yeah, they are increasing, but we do have different. Yeah, I'm just trying. If I will be in front of the blackboard, I will probably be almost here. Yeah, they are bended. Yes, that's mean at the moment we have to use, yes, thank you, Noah, for using this. They are like bended, yeah, in different, like differently. Yeah, they are just, yeah, in different direction. Okay, and of course, whichever way it's like bended, we do have a special terminology for this. You may guess the second derivative will be involved. Right? That means even without seeing the graph, but knowing the calculus and knowing the property, you probably will tell me that, oh, this is bended like down and this is bended like up. Okay, but let's see how we can, let's investigate. Yeah? Okay, the same graphs, and of course the tangent lines. Yeah, tangent line is quite good tool, quite strong tool. Ironically, it's just a nice tangent line, just touching the curve, but it's telling us a lot. Okay, let's look at this. Both of them are definitely increasing. Yeah? That means that we're not focusing on this at the moment. That means, no, we can say, if it's increasing, all of the slopes are positive. Okay, that's, we don't have any slopes are positive. And we can see definitely all of the pink lines has a positive slope. Okay, but now let's look how the slopes behaves in terms of growing or like declining the value. Okay, let's look at this. This slope, that's tangent line. The slope looks like that. I mean the tangent line and the slope. And this one is like that. It's a little bit more steep. This one is even steeper. That means, what do you think? What we can say about the slope It's definitely positive, but the slope itself is increasing. It's increasing. Okay, that means now it's nice. I mean, nice, a little bit tricky part, but I want you to tell me. How can I don't want to use the function. Actually, I can, That's what we can say. If, let's say, if f, I can say f. If f is increasing, we know that the derivative of f is positive. Make sense? Yes, of course. Yes, I know, Noah. Okay, now what you told me that this slope is increasing. Yes, slope is increasing. Then what I can say? Derivative of this must be positive. But instead of the word slope, what I can put? Like how we define the slope of the tangent? Slope of the tangent is simply, can you tell me how we define slope of the tangent? In the, slope of the tangent. I know, Robbie, you thinking ahead, which is really good, and Noah also, but just slope. The slope, yeah, we can see that slope is just the first derivative. Yes, that means instead of the word slope, I put first derivative and then again derivative. That means what is the final conclusion? Prime and prime, the second derivative. Okay, that means in order for the function to be like bended, yes, bended this way, the first derivative must be positive. Okay. And and I have everything on the bottom of the slide, but I just want you to investigate. Let's look at this slope. This slope of the tangent is like that, and then we can see it's becoming less steep, even less, and almost horizontal. That means what is happening with the slope? Is slope increasing or decreasing on this side, on the right hand side? It's decreasing. That means now let's see. If the function is decreasing, we just learned that its derivative is less than 0. Now, slope is decreasing, then derivative of the slope is less than 0. And slope, in the terms of calculus, is the first derivative. Derivative of the derivative, of course, will be the second derivative. That means in order for the function to be bended like this way, okay, I don't want like this way, the second derivative will be less than 0, negative. Okay, so let's see, I did type everything. The slope of the tangent increases, f prime is increasing, its derivative, I mean, f is that's the slope. Slope is increasing, which means the second derivative will be positive, because for the increasing, the derivative is positive. And then slope is decreasing, which means this is slope, right? That's slope. F prime. And derivative of f prime, of course, is the second derivative. Second derivative negative. Okay. And I can maybe write this, second derivative positive, second derivative negative. And now let's put, instead of bended, let's introduce a new terminology, and that's this. Okay. If we will see the function bended this way, we will call concave up. Okay, concave up. I will erase this. If we will see the function bended this way, we will call concave down. Okay. One way, did I type this? I don't even know if the textbook is providing, but I can tell you some, because sometimes we, probably not, but could be confusing. Like you will say, how do I know, even looking at the graph, if the function is concave up or concave down? Oh yeah, actually I did type this. if you will draw a function, like let's say I will draw a function, and you will try to draw a tangent line, yeah? Tangent line, tangent line, and if the tangent line is placed below the curve, always the curve is concave up. Yeah, that's the good definition. If the tangent line is placed above the curve, the curve is always concave down. Okay, that's one way to quickly like determine. Yeah? And we do have a nice rigorous like definition, and we will call concavity test if the first, the second derivative positive, function will be concave upwards. If the second derivative negative, concave downwards on the certain interval. Okay? That means now we have to test the second derivative for concavity. Also, oh yeah, I'm showing you, we will have the moment that function is changing concavity. And how do we call this point? I hope you know this. Yeah. Okay, Robbie, do you know, it's actually funny because I always have the feeling to call critical points also, but critical points, unfortunately, we just save for, we just saving for the first derivative, but they are still important points. But of course, from this slide, you can tell that we will call inflection point. And now, how can we find out the potential list of the inflection point? Yeah, inflection point. That means in order to find the potential points for the inflection point candidates, we have to solve this equation. Okay, but of course, not all of the points, not all of the solutions of this equation will give me inflection points. It's the same thing, like not all of the critical values will give me the local extreme points, okay? But in order to identify the inflection point, the point that the function is changing concavity, we have to set up the second derivative equals to 0, or actually the same thing, second derivative is undefined. Like for example, that corners, yeah, doesn't exist. That means we're doing actually exactly the same thing like for the critical points. And we will have a list of numbers, like list the solution. We also have to test the sign, yeah, the same thing. If the first derivative, that we can see B, yeah, B probably one of the solution was B, okay, was also C, and P, and I would say second derivative is not defined at D, or let's say E. Okay, as we can see, we have all of the points. But when I put on the number line point B and test the sign, the second derivative is actually negative. Yeah, because function is concave down, and then the second derivative on the other side is positive. That means second derivative is changing the sign, is changing the concavity, concave down and then concave up. We do have, that means this is definitely an inflection point. The same for C, inflection point, okay. What about D? Is D the inflection point? Is function changing concavity? What do you think? Function is concave, yeah? Oh, John is saying no, but let's see, it's concave down and then it's concave up. This is this weird, like sharp turn, but you can definitely see the second derivative is negative and positive, concave down and concave up. That means this is definitely an inflection point. And P is the inflection point because we have concave up and concave down. But what about E? Is the situation at E giving us inflection point? No, but second derivative is definitely undefined. The first one is not even, but we can see we have concave up and concave up. That means this is, we can see this will be the solution, but it will be not inflection point. Everything it's about testing the sign. Okay, that means let's take a function and let's find out everything. Increasing, decreasing, intervals, concavity intervals, and inflection points, and local extreme values. And I believe, yeah, we can take, again, just the third degree polynomial. Probably, we know like the polynomials are the easiest function. Probably the graph will be like that, something like that. But we have to find out where exactly is the position. Yeah, because polynomials are the easiest function, just a nice wave. Okay, did I type something? Okay, we need the first derivative, which will be x squared minus x minus 2. And for the critical points, we have to find out zeros. Oh, I even have the second derivative. Okay. Okay, I don't have anything else. I will write for you. That means, first of all, we will need critical points. Okay. Critical numbers. Derivative is 0 if the x squared minus x minus 2 is 0. We need to factor out, and who can tell me how we can factor out this one? We did have similar function. X squared minus x minus 2, the quadratic expression. X and 1 and 2, you typing for me, but it's negative and negative. Negative 2, I think I'm copying. Oh yeah, actually, you, yeah, everybody, oh, well, you good. Noah, John, Jack, you good. Yes, that means my critical points are negative 1 and 2. Am I right? Yes. Now what we can do, we can try to test it, negative 1 and 2. And we will test the first derivative, which is, actually I can use this expression. Okay, when we put negative 2, we will have negative and negative, positive. When I put 0, we will have positive 1, negative 2 times negative, and when I use 3, positive. Okay, that's when we can nicely see function is increasing, decreasing, increasing. Local max, local minimum value. Yeah, nice, and that's the first derivative test. Okay, now let's find out the potential critical points. Second derivative, inflection points. Second derivative is 0 if 2x minus 1 is 0. Can you tell me what is x? Just the linear equation. 1/2, thank you. And then we can put 1/2 on the number line, and I will test the sign of the second derivative, which is this one. I mean, either, yeah. If we substitute 0, it's negative. When I substitute 1, it's positive. That means now we know that function is concave down and concave up. At 1/2, we definitely have inflection point because function is changing concavity. Okay, but what we can do, we can take all of this information and put like on one number line, which I kind of did the table. Because we did have 1/2, that was the 0 of the second derivative. Negative 1 and 2 was the zeros of the first derivative. Between, we just have an interval. That means on the top, we have just the number line. Between negative 1.5, between 1/2 and 2, and 2 to infinity. Okay, now the first line, I mean the second line, because the first one is x, indicates the sign of the first derivative. And what was the sign? Let me just check. Positive, negative, positive. Positive, negative, positive. Yeah? Now the second derivative was, let me check, negative for numbers less than half, negative, 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 positive, positive, positive. Okay, and now we know that this was local maximum, and at 2 was local minimum, and that was inflection point. Okay, this is just f of -1, f of 2, and inflection point f of half. And now how the function behaves. We can even try to, function must be increasing, concave down. That means I think it's something like that. Yeah? Bended this way. And local maximum. Then is decreasing, concave down, and actually is changing. This will be the inflection point because it's still decreasing, concave up, because we can see we're changing local minimum, and then yeah, we can see nicely, we can like combine the increasing, decreasing, and of course I still don't know how high because I didn't compute the values, but maybe I can add, where is 0 actually? 0 could be somewhere here. 0, and I don't know exactly, but this will be 2, this is 1/2, this is -1. Okay, kind of like the graph. I don't know, probably I have to maybe put a little bit higher because I don't know, we can compute, but I don't know what is this value. I don't know this value, and I don't know that horizontal levels. But we don't have to focus on arithmetic. Yeah, the thing is to know the shape, the concavity, and the increasing, decreasing. Okay, that means this is nice, nice. Question. Okay, I have 2 things. Hopefully I can manage because we have, yes, we have 8 minutes. What we have instead of, because, okay, one more thing. Let's look at this part. Okay, this, what we're doing, as I said, it's so easy and so obvious, but we actually call the first derivative test. Yeah? Like in order to look if the function has local maximum, local minimum, yeah, we will check increasing, decreasing, and it's obvious, like, yeah, we can see it's obvious, maximum, minimum. Okay, but also, let's actually, I can draw it. When function has local maximum, what about concavity? Always when function has a local, like local maximum, function is concave up or concave down? It's concave down. And of course, local minimum will give me concave up. That means sometimes in order to determine local maximum, local minimum, we actually involving a second derivative, and we call a second derivative test. Okay, which means is this one. Oh, I can actually show you this. That means it's the same that I just did. Like we can see, we do have a point C. We definitely know that the first derivative is 0. That means C is a critical point. And actually second derivative will be positive, which means positive, concave up. If it's concave up, always function will attain local minimum because it's at the bottom of this. This situation is the other way. At C, we have critical point because derivative at C is 0, and function at C is concave down, which means the second derivative is negative. Then, if we satisfying this condition, function attains local maximum. We can see maximum. I would say, I think this is of course really useful tool, but I always think it's like additional things to calculate. I believe the first derivative test, first of all, works always, and it's just, yeah, just as easy to check the increasing, decreasing, and we know the situation. We don't have to involve the second derivative. But I know that some students like to involve this. You can use, but as I said, in order to determine local maximum minimum, you can just test the first derivative. But I also want to give you this as a tool. Also, what is not good about this, if you will actually try to check if the second derivative is positive or negative at the critical point C, and you're not getting a number, you're just getting 0, then the second derivative test is inconclusive. We can't really conclude. Then we can see, then we have to use the first derivative test. Yeah? Increasing, decreasing, of course, maximum. Decreasing, increasing, of course, minimum. That's the first derivative test. Okay, that means that's the second derivative. And I do have, I don't know if we can manage, we will not do this one because that's easy. I would like just do this question, okay? Because this question, this is the last question for today, and this will kind of, yeah, if you can answer these questions, you're good, okay? You definitely understood everything what I said. Okay, so you have to be really focused because I'm trying to trick you. Okay, this graph that you see, okay, is the graph of the derivative, the first derivative of the function. That's when we don't really see the function. Only thing that I can tell you, the domain for the function is all of the numbers. That's mean we shouldn't be worried to exclude any numbers, no. Okay, that means this is the graph of the derivative. Okay, and what we can do, let's say just from 0. Okay, we just have the graph from between 0 and 9. We will not go further. And now, on what intervals is the function increase? Is f increase or increasing? Okay, that means John is saying between 1 and 3, between 5 and 7, and from, yes, we can say, oh, that's 8. And now, does John gave us the good answer? This is not a graph of the function. We don't really see a function here. That means what you gave us the increasing part of the derivative. Okay, that means if the derivative, because this is derivative, if derivative is increasing, its derivative is positive. That means you gave us the answer that the second derivative is positive. Okay, and I will copy from 1 to 3, from 5 to 7, which is not even the question here, and from 8, let's say to 9. You have infinity, but it's, I understand, it's okay. That means, yeah, it's not, that means what we have to do, from 2, 4, 6, yes, I think George gave us the correct answer. That means function will be increasing if the first derivative is positive. Do you know the easiest way is to do the test? 0, 2, 4, 6 are the critical points. 2, 4, 6. And we can see between 0 and 2, the first derivative, I can use green color, it's negative. Between 2 and 4 is positive. Between 4 and 6, negative, and then positive. Okay, that means, oh, I think, George, did you say from, oh yeah, you said, okay, you know, you just saying infinity, I think it's perfectly fine because I just limit to, that means this will be infinity. Okay, I think you, yeah, that means now we can see function is decreasing, increasing, decreasing, increasing. That means that's the intervals for the increase between 2 and 4 and 6 and infinity. Yeah. Can you tell me where the function has a local maximum and local minimum value? At which x points? Can you see my arrows? Local minimum at 2, really good. And local minimum also at 6. And what about 4? At 4, a function will attain local maximum. Thank you. We can see this. Okay, and actually inflection points, that's the last part, inflection points. Yeah, we can see by accident, John gave us the good answer because John gave us the answer where this graph is increasing, which means if this is increasing, then its derivative, which is the second derivative in this case, is positive. That means, and if the second derivative is positive, the original function is concave up. Yeah, function will be concave up. From 1 to 3, okay, function will be concave up, and then will change for concave down. That's when we can see, I can maybe use the blue color for the inflection points. Wherever we have horizontal tangent here, that's when we will have horizontal tangent here, horizontal tangent here, horizontal here, and horizontal here. Yeah? That means all of the inflection points, because function is, I mean, the first derivative is increasing. This means that the second derivative is positive. This means that the function is concave up. And then when this function is decreasing, we have concave down. That means at 3, we change in concavity, at 5, 7, and 8. Okay, that's the answer for C. 1, thank you. Because I yes, I can add at the end. Thank you. Yes, thank you, John. I just ignore 1 because I start from, yeah, that means that's the inflection. That means it's really nice question because it's kind of forcing us to think the other way. Yeah. Okay, that means that's everything. You may go through again all of the questions that I solved. I think I skipped 1 question, but the solution is typed. And yeah, that will be everything. And thank you. Yes, thank you for answering all of my questions. Thank you for joining me. And please check tomorrow the section 3.2. Okay, I will put the really short video and maybe just 1 or 2 exercises. But please, yeah, please go through again my session. Don't miss any question, and good luck with your weekly assignments. And please, yeah, please stay active on the discussion board. And you can always like email me, or if you would like to meet with me one-to-one, I will be more than happy to meet and help you. Okay, thank you. And please stay healthy. Okay, please stay healthy. Okay, thank you and good night. Thank you. Thank you, David.